All right, so 6.4 is really a continuation of 6.3. So in 6.3, and I kind of continued the notes here, we looked at these problems finding the area under a curve by using some number of subintervals, which were our rectangles. So then we got either an underestimate or an overestimate of the actual area under the curve. So it turns out that what we can show is that if we take one of these Reimann sums, so this looks a little complicated, but it's really not as bad as it looks here. So this is one of these Reimann sums, so I can refer back. That's why I kind of made this one an extension of the previous section. So look back up here. See how we created, this was a Reimann sum, okay, to estimate the area underneath this curve. So remember what we had here. These were the delta x's. These were the f of x sub 1. This one's f of x sub 2. Delta x again. Okay, so I can write that Reimann sum out generally like this, right? This is just the length of the rectangle, the height of the rectangle, length of the rectangle, height of the rectangle, length of the rectangle, height of the rectangle, etc. Okay? So what this says is it says take the limit as n goes to infinity. So n is the number of rectangles, okay, or the number of subintervals. So what this is saying is if I let the number of rectangles go to infinity, in other words, every time the number of rectangles increases, I'm getting a more and more accurate estimate of the area actually under this curve. So if I let that number of rectangles tend to infinity, I'll actually get the precise area under the curve, okay? And so it turns out that this limit is equal to the integral, and this is called a definite integral. Okay, definite. So far we've been looking at indefinite integrals. Okay, those are the ones without the endpoint. So you see how this is an integral from a to b. This is called a definite integral. So it can be shown that if I take the limit as n tends to infinity of one of these Reimann sums, that's equivalent to the definite integral from a to b of the function f of x. So that's just kind of what I wrote out down here. So what did I write out? I said, this says we can find the precise area under a curve by letting the number of rectangles n go to infinity, and that this area is equal to the indefinite integral of f of x from a to b. Now, this is assuming that f of x is non-negative. Okay, so let's take a look at some of these functions. So what I thought we would actually do is look at this same function, f of x is 3 minus x, on the interval 0 to 2. Now, that's what we did up here. So again, I'm referring back. So here was the example that we did in the previous section. And we said, for that function, we estimated the area using the left endpoints. We got about 4.4. Then we estimated that area using the right endpoints. Got about 3.6. And so we said, all right, that must mean the actual area would be somewhere in between 3.6 and 4.4. So what we're going to do now is we're going to use the indefinite integral. So we're going to say the area actually under that curve, using this definition, is the integral from 0 to 2 of the function with respect to x. Okay, so now I integrate. So 3x minus a half x squared. Okay, here's the notation. I evaluate from 0 to 2. So what I just did, if you want a technical explanation, as I use, we would call this the fundamental theorem of calculus. So this just says that to do an integration, to evaluate an indefinite integral like this one, okay, it says, well, what do? I find the antiderivative, so that's what I did, the 3x minus a half x squared. And then I evaluate from 0 to 2. So how do I do the evaluating? Well, I actually just plug the endpoints into the antiderivative here, and I do a subtraction. So look, I'll just illustrate this with the example. Okay, so I already have my indefinite integral. Now I'm going to evaluate. So what I'm doing here is I'm plugging the 2 in. Okay, so I have 3 times 2 minus a half times 4. Okay, that's this piece. Now I subtract, and now I have to plug in the 0. And so that's this piece, okay? So that's that fundamental theorem of calculus, but it's actually pretty simple. Okay, so now I just evaluate, so what's that, 6 minus 2 minus 0? So that means that the actual area under that line between 0 and 2 is 4. So does that make sense? Well, look at that. We said the actual area must be in between 3.6 and 4.4. So that's exactly halfway in between. So that makes perfect sense. And that's, of course, much easier than actually doing this problem by using the approximating rectangles. Okay, so now it becomes really easy to find the area under any curve as long as I'm able to estimate. So I'm using this definition again, same one, this one. I'm saying, okay, to find the area under the curve, all I do is I set up my definite integral. I'm going to keep using this terminology. It's a definite integral. Okay, and so it's from 1 to 3, those are the limits. There's my function. So first thing I do is I find the antiderivative. Okay, so the antiderivative is what? X cubed plus e to the x. And I can check that. If I differentiate that, it's 3x squared plus e to the x. Looks good. And then I evaluate that from 1 to 3. So that's what? So then now I'm using this. Okay, so I'm saying to evaluate that, I plug the top limit, the upper limit in. It's 27 e cubed. And then I subtract, I evaluate at the lower limit. So 26 plus e cubed minus e. So there's the exact area under that curve, this one. Okay, in between 1 and 3. Now, I mean, if I wanted to, I could put that in a calculator. E is 2.7-ish. I could use the E to the X button. But I'll go ahead and just leave the answer in exact form. It's the exact answer. Okay. Same thing. Find the area under f of x is 1 over root x on 1 to 4. So that's the integral from 1 to 4, x to the negative half dx. Okay, evaluate from 1 to 4. So 2 square root 4 minus 2 square root 1. All right, so those are finding the area under a curve. I mean, these are the same thing. But in this part, we're just looking at, we're not even going into the interpretation. We're just actually evaluating these definite integrals. Okay, but same idea. So what do I need to do? I need to say, okay, find the antiderivative of this integrand. So what is that? A fifth x to the fifth minus 2/3 x cubed plus 3x. Check and make sure I got that right. 5 would come down. 5 times a fifth is 1. X squared plus 3. Looks like it. Okay, then I evaluate the upper limit. So that's fifth times 1 minus 2/3 times 1 plus 3 times 1 minus a fifth times 0 minus 2/3 times 0 plus 3 times 0. Okay, this of course goes to 0. So what is this? An LCD, I guess 15. So this is 3/15 minus 10/15 plus 45/15. Okay, so 3 minus 10, negative 7 plus 45, I get 38 over 15. And so again, if I wanted to, I could put that in a calculator, get a decimal, but that's a nice exact answer. Excuse me. Okay, so what about number 2? Okay, so let's see. I could move that 3 out front if I wanted to even. Really what I'm integrating here is 1 over x. So I know the integral of that is ln of x. Evaluate from 1 to e. Okay, so do you remember how these ln's work? So ln of e, that's the same as log base e of e. So this is saying e to what power makes e? The answer is 1, right? So this is 3 times 1. And then what about ln of 1? So e to what number makes 1? 0. So the result is just 3. Comes out nice. Okay, what else is there? Okay, integral -1 to 1, x squared minus 1, quantity square with respect to x. Okay, so I think in this one I would actually go ahead and square that quantity. FOIL? Okay, because it's going to be really easy to integrate in that case then. Okay, so let's see. Now my integral, so what is that going to be? X to the 5th over 5 minus 2/3 x cubed plus x. Can make sure I got that right. If I differentiated that, get x to the 4th minus 2x squared plus 1. Looks good then. And -1 to 1. Okay, and then I plug in my limits. Get the upper limit, 1. The lower limit, -1. Make sure I got all those right. So +1, +1, +1. The -1 to the 5th is -1. -1 cubed is -1 times negative is positive, and then -1. Okay, so it looks like it. Okay, let's see what this is going to give me. Okay, so I'm going to have a 5th plus a 5th. Looks like it's going to be 2/5. And what else do I have? I have -2/3 minus 2/3. So -2/3 minus 2/3. So what is that? -4/3. And then I got 1 minus -1. So 1 plus 1, 2. Okay, so then I guess I'll do an LCD. So 15ths again. So that's, let's see, multiply by 3, 6/15. And then by 5. And then 30/15. Okay, so 10/15 plus, is that 16/15? Make sure I got that right. Looks like it. Okay, what else is there? Let's do a little application problem. The rate at which radios are assembled by the average worker T hours after starting work at 8 a.m. is given by this quadratic function. And so the question is, how many radios are assembled by the average worker by, say, 9 a.m.? Okay, so what I actually have here, I have the derivative function, right? Because this is a rate. This function gives me the rate at which the radios are being assembled. So I don't know, should I use like maybe the letter N for the number of radios? So as far as the actual number of radios being assembled, well, that would actually be the antiderivative or the integral of the rate at which those are being assembled. Okay, so this is a number. Okay, so let me look at, well, what is this asking specifically? This is asking by 9 a.m. So we're starting at 8 a.m. Okay, so this is saying T hours after starting at 8 a.m. So if I want to know what happens between 8 a.m. and 9 a.m., aren't I looking at the integral from 0 to 1? So this would be the number of radios assembled from 8 a.m. to 9 a.m. by your average worker. So let me do the integration. So what is that? Negative t cubed plus 6t squared plus 15t. Double check that. That'd be negative 3t squared plus 12t plus 15. Okay, evaluate. The limits are 0 and 1. Plug in the 1. And then the 0 is going to be 0 all the way across. So what is that, 20? Right, so the number of radios assembled from 8 a.m. to 9 a.m. by the average worker is 20. Okay, and there was one more part. It said, what about from 10 a.m. to 11 a.m.? Okay, so that's the same thing, but now I'm integrating from, let's see, 10 to 11. So 10 is 2 hours after 8, 11 is 3 hours after 8. Same function, right? And we already did the integration. It was negative t cubed plus 6t squared plus 15t. Evaluating from 2 to 3. Okay, this part's more interesting. So then I plug in the 3. 6 times 9, 45. And then subtract. I plug in the 2. Okay, hopefully I got all that right. So that's what? 27 plus 45. Let's see, what is that? 46? 8, 16 plus 30 looks like it. So this is 26. Okay, so from 10 a.m. to 11 a.m., the average worker assembles 26 radios. So they have sped up there.